The first accurate three-dimensional map of our Milky Way galaxy shows that it's warped and twisted. A report in the journal Nature Astronomy claims this warp spiral pattern is being caused by torque off the spinning of the Milky Way's massive inner disk of stars. The new observations are based on the positions of 1,339 Cepheid variable stars, which were used to map the Milky Way's real shape. They found the Milky Way's disk of stars becomes increasingly warped and twisted the further away the stars are from the galactic center. One of the study's authors, Professor Richard de Grace from Macquarie University, says people usually think of spiral galaxies as being flat disks. The problem is, trying to determine the real shape of our galaxy is a bit like standing in the middle of the woods and trying to determine the exact size and shape of the whole forest. It's also notoriously difficult to determine distances from the Sun to some parts of the Milky Way's outer gaseous disk without having a clear idea of what the disk actually looks like. However, over the past 50 years or so, there have been some tantalizing hints that the hydrogen clouds of the Milky Way could be warped. From a great distance, our spiral galaxy would look like a thin disk of stars that orbits roughly once every 250 million years around the central region, where hundreds of billions of stars provide all the gravitational glue needed to hold the galaxy together, apart from dark matter, that is. But it now seems this pull of gravity is far weaker in the galaxy's far outer disk. There, the hydrogen atoms making up most of the galaxy's gas disk are no longer confined to a thin plane. Instead, they give the disk an S-like or warped appearance, caused by the huge amount of torque coming from the spinning of the Milky Way's massive inner disk of stars. The key to developing this new three-dimensional map was a recently published catalogue of young variable stars known as classical Cepheids located in the warped Milky Way disk. Data on these stars was provided by NASA's WISE, Wide Field Infrared Survey Explorer spacecraft. The authors were able to use 1,339 of these Cepheid variables to help them develop their map, and this allowed them to determine the twisted appearance of the galaxy's far outer regions. Classical Cepheids are some 4 to 20 times as massive as the Sun and up to 100,000 times as bright. Cepheid variables pulsate, that is, expand and contract, at set rates based on their intrinsic luminosity, and so they can be used as standard candles to measure cosmic distances. Because astronomers know how intrinsically luminous a Cepheid variable star is, because of its pulsation rate, they can determine how far away it must be. It's exactly the same as looking at a row of streetlights down the road. You know they've all got the same brightness, but the ones further down the road will appear dimmer than the ones nearer to you. This allows very accurate distances to be determined for these stars, with an error of only 3 to 5%. The new research provides a crucial updated map for studies of the Milky Way stellar motions and the origins of the Milky Way's disk. De Grace reminds us that most of the matter in the Milky Way is dark matter, which is an intrinsic part of our universe. But de Grace also points out that not only do scientists not have any idea what dark matter is, they're not even sure exactly where it is. The new research showing the real shape of the Milky Way could help scientists better determine how dark matter is distributed around the Milky Way galaxy. The authors were also surprised to find that their three-dimensional collection of 1,339 Cepheid variable stars and the Milky Way's gas disk showed the stars tended to follow each other closely. De Grace says the discovery offers new insights into the formation of the Milky Way. He says perhaps more importantly, he found that in the Milky Way's outer regions, the S-like stellar disk is warped in a progressively more twisted spiral pattern. Astronomers have observed dozens of other galaxies which have shown similar patterns. De Grace says that means the Milky Way's twists are rare, but not unique.
What we found is that towards the outer regions of our Milky Way galaxy, our galaxy starts to deviate from a flat pancake shape. Now, that was known for a long time in its distribution of gas, and by gas I mean hydrogen atoms, of which we knew for the last 5 decades or so that in the outer regions the hydrogen gas would deviate from the plane, become higher on one end and lower on the other end. Now, our study, among the results that we found for the first time that the young stars in the Milky Way, traced by so-called Cepheid variable stars, which are quite massive and therefore quite young, follow that same kind of warped distribution where there is a clear deviation from this flat pancake shape. But that's not everything. Also, what we found is that the main direction of this warp is not a straight line, but it starts to more or less trace a spiral structure as we go further and further out, in the sense that this warp becomes twisted. at greater and greater radii.
Is this anything to do at all with the talk on stars within the galaxy caused by the galaxy's rotation?
Yeah, so our interpretation of this result is that the massive disk of stars making up most of the Milky Way is rotating around the center of the galaxy every 250 to 300 million years, and it's dragging behind it the outer layers, which are less strongly gravitationally bound to the Milky Way because they're much further out. And so that rotation in the warped outer disk is slightly lagged behind.
Is there any connection between this warped structure and the thick and thin disks of the Milky Way? Is there a correlation there?
That's a good question, but we haven't actually looked at that. Now, having said that, the bulk of the stars in our Milky Way are distributed in the thin disk. That's really the vast majority of stars. The thick disk is puffed up somewhat, and it tends to extend to greater radii, but at much lower numbers of stars than the thin disk. The warped distribution of stars would deviate from this thin disk into the realm of the thick disk. So there might be some dynamical interaction, but I would say that the warp itself originates from the thin disk and is probably most closely associated with the thin disk. I don't think that this has to do with the spiral structure of the Milky Way as such, because it's quite well known by now that the longevity of these spiral arms is due to something called density waves, where stars move around the center of the Milky Way and they get attracted by the higher density of material in the spiral arm. So they move faster towards the spiral arm, spend more time there because of gravity, and they move out slowly. And in between the spiral arms, they don't spend much time. That's the density wave theory. I think that is a difficult, that's a completely different dynamical process. In this particular case, we believe that we really see this gravitational torquing, the dragging behind of material by the inner massive disk.
What do you need to do next for your research?
Well, there's a couple of things that we can do. First of all, we looked at about 1,300 or so of these Cepheid variables. That's a sizable sample, but it can always be improved. One of the problems with our sample is that all of these stars were located on the near side of the Milky Way center, so on our side of the center. It would be great if we could get similar quality data on the other side of the Milky Way center so that we could see whether or not the features that we have found are symmetrical. And that is more than just an academic exercise. The idea here is that if the warped distribution of the Cepheids and the twisting is symmetrical on either side of the Milky Way center, then we truly have a process here that works across the galaxy. Colleagues have suggested that what we've seen might have been caused by the infall of a dwarf galaxy towards the outer regions of our Milky Way. And if that's the case, you would only expect it on one side. So that's one thing that we would like to explore. Another thing, of course, is that you probably know very well that the European Space Agency is currently operating its Gaia Satellite, which is meant to determine positions and distances to about 1 billion stars in our Milky Way galaxy. The first data release has come out. The second release is due soon, but the full data set will not be released for another 3 to 5 years. By that time, accurate 3D map of our Milky Way galaxy, and hopefully our result will serve as a benchmark to hold those Gaia results against. And then finally, the other the quite exciting prospect here is that by constraining the distribution of stars in our Milky Way more carefully than before, we may have a fighting chance of determining where all the dark matter in our Milky Way is located. And that's still a big open question.
That's Professor Richard de Grace from Macquarie University in Sydney.